Hello everyone, welcome to another edition of Learning Glass Studio with me, your professor. Today we're going to talk about collision rates and applications of collision rates to transport and chemical reactions. And when we talk about collision rates, the most intuitive, simple but intuitive yet powerful is to use kinetic theory. So kinetic theory is based on particles moving around at a given velocity. And most of the time when we talk about kinetic theory, we're using the Maxwell distribution of energy and velocity. So that's what we're going to do today. And the level of detail we're going to go into is that these particles are colliding, and we're going to ignore any interactions with that. And the way to do that is to use hard spheres, where they just approach each other based on their size. They just have elastic collisions. And then, so in terms of their size, we can start with asking the question of if these particles, what determines if these particles collide? One of them is their size and velocity. So if we have an area in space, and if we're talking about three-dimensional space, this would be a volume in space whereby things will happen. So this volume would be the volume at which this particle here, this hard sphere that could be a molecule of some diameter A, is mixed in with either itself, molecules of its same molecule type but different molecules, or today we can talk about what if they're different sizes, or a different molecule, and that different molecule has a different size, because as we know on the periodic table, atoms have different sizes, different mass, different sizes, and chemical reactions occur because of that. And or the reactions occur from different interactions, and part of that interaction is their size, is their collision. So this is two different molecules, molecule A, molecule B. They happen to be a different size, and because of their size, there's a limiting volume that you can define. So if this particle is moving this way, this particle is moving this way, there's this collision volume here determines if they will collide or not. So if the particle centers are within this volume, they're going to collide eventually because they're moving at a certain proximity to each other, and this is the limiting case where they just graze each other. There's this, it might not be a direct impact, but there's some touching contact of their hard spheres, and the limiting case would be this sphere. So anything within that, there's going to be a collision. Okay, so collision will occur if molecule centers of the sphere lie within the collision volume. Okay, so this collision volume has a diameter the diameter is related to the size of these spheres. So if this is the center of the axis of this cylinder, so one part of the radius is this radius, and the rest of this, the distance where a collision will occur is determined by this radius. So the diameter is related to the radii. This is the radius. Okay. So the volume swept is related to the geometry of this cylinder, of course. So the area of this cylinder times the velocity of this situation, this relative velocity, would give you the volume swept. So the area of the cylinder is known. So this is the volume swept per time. Volume sweep rate. Swept, sweep, maybe sweep is better. This is how much volume is occupied or like crossed. Sweep meaning you cross it over, you move in space over this volume. Okay? So this is the diameter of that cylinder that we're talking about. An interesting thing is that by convention, note, a very important note that can be confusing because what we're talking about is a nice intuitive cylinder saying will these particles collide? Yes, they will collide if they're close enough. How do we quantify how close they are? It depends on the size. So if the particles are bigger, then there's more of a chance they'll collide because there's more a bigger sphere to a bigger target. So that's what we're talking about here. Depending on the size, there's a volume which will determine whether they'll collide. So that's nice that we can picture. And this cylinder has a diameter given by, related to the diameters of the particles. But there's a definition called collision diameter. By convention, there's something called collision diameter. This is the effective volume of colliders. The symbol is called, I'll draw the symbol like this. So, okay, I'll draw it like this. Sigma AB is the collision diameter, and it's related to the radii of. So that's one good way to think about it. The effective volume is the effective diameter here. Effective diameter of colliders. So what we're doing is we're taking the radius of the first one, the radius of the second one, we're adding them together. So that gives you an effective diameter where you can collide. But it's also the radius of the collision volume. So this D we drew here is not the collision diameter. The collision diameter is the radius. So if D is this diameter, D over 2 is the collision diameter. So that's one thing to keep in mind. Okay, so let's keep on talking about this collision rate or collision frequency. Z it's the number of you can find it if you know the number density, so the number of particles per volume times the volume sweep rate. So by multiplying those together, you would cancel out this volume, you would get the number of particle collisions collision volume swept, I should say. This volume here. That'll give you the number of particles colliding per time. Okay, so this volume sweep rate is related to the relative velocity. So for the volume, for relative, we're talking about two different particles moving at their respective velocities. So the relative motion would give you a slightly different formulation of the sweep rate. That would be related to the area of this cross section, and then we're going to express it in terms of this collision diameter. So the collision diameter is the radius of this. That's going to give us the volume. And then because it's relative motion, you have the square root of 2. And this is the relative velocity. So this is relative motion. And this is the median diameter. It's a velocity. I mean, the median velocity, it's the fact that you have a distribution. So let's go up here. So from the Maxwell distribution of energy, and which is quantified in terms of kinetic energy, which is given by, quantified by velocity, we have shown in class before that you can describe a population of particles moving, and if we're talking about two different particles and some relative velocity of that, you can express this in terms of the mean velocity where mu equals the mass of molecule A plus the mass of molecule B. That's the reduced mass. Okay. So we have these particles colliding. In terms of the hard spheres, we are saying that this hard sphere radius determines a volume that they sweep, and the collision frequency depends on that volume and the number of density of particles in the whole space you're considering. And then we define this collision diameter, which is the related. It's making up a diameter of a sphere based on the particles that are colliding. So it's related to the diameter of the. It's one you're making one diameter out of these two radii of the colliders, and that the same thing is in terms of what this collision volume is. It's the radius. The collision diameter is the radius of this collision volume. Okay. So when we put this together, for A colliding with B, you can get an expression of this collision rate like this. The number, if you're talking about A colliding with B, that depends on the number density of B. The sigma here. And it depends on the velocity of A. But if you're talking about total collision rate per volume, we're talking about all both A and B. So per volume would be dependent on both concentrations. The number density of A and the number density of B contribute. And their relative motion in terms of this relative velocity is what contributes. Where this can be given from the Maxwell distribution. Okay. So let's use this. So the mean free path is another way of thinking of the collision frequency. It's more common than collision frequency, actually. It's what a lot of physics is determined by, or the way that they hallmark, or the parameter that tells you which regime you are in is related to the collisions, and the way that it's quantified is in terms of the mean free path. And what it is, it's the length traveled before next collision. So you can see it's related to the collision frequency, because the collision frequency will tell you how many collisions occur per time. Another way of thinking about that was, okay, how much distance is traveled before a collision? And the way that it's related is it's saying that the distance traveled depends on your velocity and your collision rate. So this is, the distance per time, length per time, divided by number of collisions per time. So the time cancels out. That gives you length of distance traveled per collision. And typically, the scale of this distance is nanometers. Okay. So we can plug these in, velocities that we know from kinetic theory and collision rates we know from kinetic theory. The next question is, for this mean free path, VA is, we're talking about the mean free path of A. So that depends on the velocity of A, or I should say here, this is in general, it depends on the velocity and collision frequency, but for mean free path of A, that depends on the velocity of A, so the mean free path of A, you need the velocity, mean velocity of A, and colliding with all mixture. So you would write that as the mean free path of A So if this mixture is just A and B, you'll define its collision diameter like this, and it depends on the total number density of A and B, and this relative velocity term. So this is basically the collision diameter, the collision frequency, and the velocity cancels out from the top and the bottom. And for ideal gas, you can express this in terms of temperature and pressure. And that's typically on the order of nanometers. So for example, if you make air one molecule, that's an oversimplification, but air one molecule colliding with itself, the way that you would do that, you would say that air is oxygen and nitrogen. And so you can describe that in terms of the pressure and the temperature, number density, but the collision diameter can be given by some average diameter of contributions of the air and the nitrogen. And when you do that, you get a typically 60 nanometers at atmospheric pressure and temperature. Okay, so other applications, applications of that mean free path are numerous. Okay, so one application is the mass diffusivity. This coefficient in front of Fick's law is saying that if a particle is colliding, if there's more particles, the number density is greater here than the number density is greater here, there's going to be some flux due to these collisions in this volume. And the net result is over space, there's going to be some dispersion of the concentration from high concentration to low concentration until and you won't be able to see that anymore in terms of a difference in concentration. The particles will still collide, but over time they will even out in space. And the rate that occurs is quantified by the diffusivity. And from kinetic theory, you can relate that to the mean free path and the velocity of the specific species you're looking at. So for A in B, dAB would be the velocity of A times the mean free path of A related to that. And if you had B in A, you would have that. Okay? So, and you can apply these kinetic theories to get the velocities and Maxwell distribution to get the velocities and so forth. Okay, now let's talk about chemical reactions. So for a chemical reaction to occur, the way that it happens is you have to literally have two molecules that can potentially react to form a product. The first criteria for that to happen is that these particles have to see each other. So how do they see each other? Well, they're within this collision volume. That's how they see each other. They are bouncing around in space. For gas phase, they even bounce around less because the number density is less. So if you're in the gas phase, they bounce around at a given collision frequency depending on the number density and the size of this volume, which is related to the size according to this theory here. So let's talk about chemical reaction rate. So if we have a reaction, A plus B goes to C plus D, let's say this is a elementary, meaning is an elementary reaction, meaning that it actually describes molecules approaching each other and colliding. You can have a global reaction where it's just a summary of a bunch of different steps of collisions, and this global average does not describe that literal molecules colliding. This one is elementary, so it does describe a simple step where these particles collide with each other. So for an actual, this reactant here, A, for it to be consumed, you have to meet some criteria. So the rate at which it will be consumed depends on the number density, of course. So this is the number density of part, where it says that the more collisions occur, the faster it will be consumed, because they have to see each other first. The faster they collide, the more they see each other, the more it's going to react. But chemistry has a lot more criteria to be met before this can be converted to products. So the rate, so the dA dt depends on the rate, depends on basically the collision rate, and some chance. This is not the only factor. You also have to, by chance, meet some other criteria, which does not happen every time, and it's very hard to quantify that rigorously, so you have to go to chance, to rolling the dice. Probability. So the probability, of course, is between 0 and 1 by definition. By definition, it's either going to happen or it's not going to happen. And 1 would be it's always going to happen, 0 will be it's never going to happen. And probability means it's somewhere in between. There's a chance. And what that depends on is, in chemistry, the way that they've quantified that is by these two factors here. So this P is the steric factor. This and the steric factor has to do with the geometry of your molecules, like the diameter and the actual structure of the molecule. And the orientation of the collision. So if you have a water molecule, the steric factor keeps into effect the fact that you can approach with the oxygen side, or you can approach with the hydrogen side. That's what this tries to keep track of. And this here is the activation energy. EA is activation energy. So it's actually an empirical curve fit. Arrhenius, the scientist who came up with this concept, one of our geniuses of mankind who helped us to proceed in the civilization and technology, he came up with this equation just by making observations and fitting curves to his observations, which was a breakthrough at that time. But now that we understand more what this process, we realize that it's a good way to model and keep track of what's going on, but it doesn't answer the question why. So the one way to describe why is that reaction, or going in that direction. It still doesn't answer why, but it kind of, it's saying that it all depends on the probability. So reaction will proceed if particles collide, of course, and by chance an energy threshold is reached. So particles collide, that should say collide. Particles collide, but that's not enough. You have to meet some additional criteria that if they collide, there's only a certain chance that you'll reach an energy to get the reaction going. That's what the activation energy is taken into account, and then this has the collision also depends. Successful collision for reaction also depends on the geometry, the shape of the molecules, attraction, all that stuff. Okay. So how do we quantify that? Well, we know how to quantify the collision rate, so that's gonna be a part of this factor. And depends on the number density. That's what these brackets are. That's what the concentration. Okay, so this is related to number density. You know, this is molar density, I guess you can say. So what is this K? Well, this K is keeping track of all these other extra criteria. So for a chemical reaction rate coefficient, it's called the this K is a function of temperature, and from collision theory, you can relate that to the collision frequency, as we've been discussing, which depends on the collision diameter, the mean relative velocity, and then these steric factor and this probability, this activation energy concept. So that's what we're saying. This is all of that stuff. The actual part of this collision rate depends on how much they collide. This is the collisions part. And the chance that they will meet additional criteria. And if you put this next to the concentrations, that's the number density part of the collision rate. So notice, this is between 0 and 1. The probability is between 0 and 1. So the physical limitation of all chemistry known to history of mankind and alien kinds, it doesn't matter, that max probability equals 1, of course. So fastest reaction rate possible for a given reaction is collision rate. So that's the physics. We talked a lot about people, you might be scared of chemistry, which is scary. But if you want to know the fastest possible reaction rate for two given reactions, it cannot possibly react faster than the rate at which they can see each other. Because that's the first thing that needs to happen. They need to collide with each other first. Then, even if they do collide, they may not react because there's some energy threshold you have to meet, and it depends on the orientation that you approach each other. So the maximum that this can succeed from reactants to products depends on those factors, and if we can say that, okay, let's assume that all of these other criteria will be met, you still have to see each other. So the physical constraint in terms of the chemical reaction rate is given by the collision rate. That's important because A, it gives you some nice insight into what's happening in the physical world, and B, like I said, it's a valid exercise, and it might be very useful to just apply this curve fitting to do some experiments to see it when this reactant is consumed, and then fit an equation to get this EA and other parameters, and that might work in some cases. But if you wanted to physically describe what's actually happening, your actual rate coefficient that you come up with, if it's a physical, real model, it has to match this, this constraint that you cannot passively have a reaction rate coefficient faster than these particles can collide. You can, however, violate this, but it no longer becomes a physical model. It becomes an empirical engineering solution, which might work for one situation, but it doesn't have any physical meaning. It just has some numerical, empirical relationships, some relationships that you can use for a given situation, but it doesn't describe the physics. The physics is that if you're talking about an elementary reaction step where these molecules have to collide to react, that's what's happening in real life. You have to first consider how much they collide, depends on their size, and the fastest that they can possibly react is given by their collision frequency, which from the hard sphere assumption, you can relate to this collision diameter and all that. Okay, so that's all I wanted to cover today. I'll see you next time.